carrying on this look at locus of the complex numbers. But how do we deal with functions? So we have some complex number as a function of another complex number, and we have to find the locus of it. What picture is it? And they usually give us some condition. The general idea when I'm approaching these problems is I try and make the condition, whatever they're giving me the condition, the subject of the function, and it's usually easier to deal with. Some ideas that appear a bit. For instance, they might give us the condition that one of the complex numbers is purely real. Well, that gives me two ideas to play with straight away. If it's purely real, then I know the imaginary part is equal to 0. I could play with that idea. The other thing I know, well, its argument would have to either be 0 or pi. Maybe I'll play with that idea. And the flip of that is, suppose they told me it was purely imaginary. In that case, I know, well, the real part would have to be 0. Or the argument would be plus or minus pi on 2. The other one that you might see is something like this. If we have the arguments, and then it's some linear function over some linear function. You see something like that. And it's equal to some number. That locus will turn out to be an arc of a circle. Now, depending on the size of theta, if theta is bigger than pi on 2, then it's going to be a minor arc. If it's less than pi on 2, it'll turn out to be a major arc. And if it's equal to pi on 2, well, we've got a semicircle. But there's some common ones to keep an eye out for. Obviously, there are all sorts of other ones we could have, but there's some of the more common ones. All right, something like this. We want to know what W is going to turn out to be. Here's the function we're substituting in. We're going to substitute into z plus 2 on z, but now we're not saying, hey, we're only going to substitute real numbers in like we have been doing in the past. It could be any complex number that we're substituting in, and the answer could now be a complex number as well. The condition is, I'm only going to substitute in complex numbers that have a modulus of 4. What would the answer be? So they've told me, here's the function. W is equal to z plus 2 on z. I'm going to input every number that's lying on this circle, because we know modulo z equals 4 would be a circle. So every point on that, we're going to substitute into this function, and we're going to get some new picture. Now here's our problem. You see, when we were just dealing with real numbers, it was really easy. We inputted one value, usually an x, and we outputted one value, usually a y. And then we could just draw a nice picture on our two-dimensional plane. But now when you think about it, we are inputting two pieces of information, a real value and an imaginary value. And it's going to output two pieces of information, also a real and imaginary. So that's 4 pieces of data. And unfortunately, we can't do that in our world. How do you draw a 4-dimensional number plane? Well, you can't. So this is how we do it. We think of it then as two different 2-dimensional ones. We have an input graph and we'll have an output graph. And that allows us to plot 4 pieces of information. So if we apply it, well, let's imagine the first number I put into our function is the real number 4. If I substitute the real number 4 into this function, I get 3 on 2. Okay, the output is 3 on 2. Well, what if I picked this purely imaginary number up here, 4i? If I input 4i, I end up with 1 minus I on 2. So I get that point. And then we'd be doing that for every single point, and we want to know what we get. Well, that goes back now to the condition they gave me was the modulus of z equals 4. We know every input is going to satisfy that. We want to know what's the output. I'm going to try and rearrange this formula and make z the subject, because that's the condition I know. I know the condition on z. All right, playing around with it. Eventually, here we go. Z is equal to 2 on w minus 1. But I know the modulus z is equal to 4. There's my new picture. It must be that. 2 on w minus 1, or the modulus of it, is equal to 4. Now if I play around with that, I can get something I recognise. So, well, the modulus of 2 is 2, and turning both sides upside down, aha, it is also going to be a circle. Centre at 1, radius a half. So there's the output graph. Interestingly though, if we were to input points in a anti-clockwise order. The output actually ends up being plotted in a clockwise order. That just doesn't happen for all functions, but it's just an interesting one for this one. It doesn't necessarily get plotted in the same rotation. It could be going the other way around. My locus turns out to be a circle, centre 1, 0, radius a half. In other words, there's the equation, x minus 1 squared plus y squared is equal to a quarter. Let's try this one then. Find the locus of z if there's the function we're substituting into, w is equal to z plus 1 on z minus 1. This time they've put the condition on the output. So all the answers we get are going to be purely real numbers. Well, I don't need to reorganise it. It's already got w the subject. I could do it algebraically. So if I did that, the key piece of information here, if w is purely real, I know the imaginary part is equal to 0. I want to find the imaginary part of this number. So I'll multiply top and bottom by the conjugates. I don't bother expanding this whole thing out and grouping them together. I don't need to, because we're saying simply that the imaginary part is equal to 0. I'm only interested in the imaginary part. All the rest, I don't care. In fact, I don't really care about the denominator. Because if I've got a fraction equaling 0, it's got to be the top of the fraction that equals 0. So really, I just need to look at this, the imaginary part of the numerator. So we have minus x plus 1 times y and x minus 1 times y. That equals 0. That's a lot easier to handle. I end up with, it simply just comes down to be y equals 0. It's y equals 0, but remember, always go back to the original question. If you think about that, y equals 0 is the x-axis or the real axis. So the interesting thing about this function is, if I want answers that are purely real, I've got to substitute in numbers that are purely real. That's what this is basically saying. However, bottom of the fraction can't equal 0. That's still a rule. That rule hasn't changed. And 1, when I substitute in, would give me that problem. And 1 is a real number. So I have to exclude it from this one. So it's going to be y equals 0, but excluding, well, the 0.10 or the number z equals 1, however you want to write it down, but there is definitely an exclusion. So we're saying bottom of the fraction cannot equal 0. That rule still applies. The other way we could do it is geometrically, using the other idea. So if w is purely real, then I know the argument is either going to be 0 or pi. We think about it geometrically. So the argument of z plus 1 on z minus 1 is either 0 or pi. If I play around with those arguments, we're saying the difference in the arguments when I draw these two vectors is going to be 0 or pi. If I join z up to both -1 and 1, the vectors that I end up getting are either going in the same direction or opposite directions. And that basically tells me it must be collinear. It's got to be a straight line. Only way I could place z and satisfy that. Have a look at this. If v was equal to 0, so I've got these two complex numbers, z minus a minus the argument of z minus b, then the point must be on the outside of those two starting points. Because if you have a look at it, I start one vector at A and one vector of B, and there's no difference in their arguments, they've got to be running in the same direction. Therefore, they must be on the outside of the 2 points. I mean, they could run the other way as well, and I'd be on the outside, but I couldn't be inside the 2. Let's plot that on our graph there. So we are on the outside. But the other case was it's equal to pi, and that's when z must be in between. If z is in between and you join them up, those vectors are running in opposite directions. So the difference is pi. We're also in between. We end up with y equals 0, same as we got before, but excluding 2 points, because when we draw our rays, we exclude the starting points. Well, hang on, I've got a different answer to the way the other one. But again, you go back to the original question. Let's have a look at those 2 points we think we're going to exclude. Well, the only one I exclude is the one from the first answer, 1, 0. Answer the original question. Look at these 2 points of exclusion. If it's positive 1, I'll get 0 on the bottom of the fraction. So yes, I'm right to exclude that. But if it's negative 1, I get 0 over negative 2, which is 0. And 0 is a real number. That's not a problem. It satisfies the equation, so I don't exclude it. Right? Because remember what we've done here. This was the original question. We transformed it into a different question so we could go and solve the problem. If the question had simply been the argument of z plus 1 on z minus 1 is equal to 0 or pi, then yes, the answer to that one is we exclude these 2 points. But that wasn't the original question. That's what I changed the question to make life easier for myself in solving the problem. Always go back and make sure you're answering the original question, not the question you changed it to. Alright, let's do one of these. Argument of z on z minus 4 is pi on 6. So this is the one where you got argument and then inside linear function on a linear function. I know that's an arc of a circle. Okay. Argument of z on z minus 4, which I could split up into be the argument of z minus the argument of z minus 4 is pi on 6. So it's similar to that last one. When it was 0 or pi, it was collinear. If it's any other angle, it'll end up being part of a circle. In this case, it's pi on 6. Well, I've got a vector coming from 0, and I've got a vector coming from 4. And we're saying the difference between the arguments of these two vectors is pi on 6. Where are we? I know it's going to be the arc of a circle. That means the line joining 0 to 4 would be the chord of the circle. And the question is then, is z above or is z below? Which arc is it? See, one side of the chord will give me the major arc, one side of the chord will give me the minor arc. This is how we can tell. A's on top, B's on bottom. I have to go from A to B, and I do it anti-clockwise or counterclockwise. How do I do that? Well, if A's here, and B is on the right, in order to go from A to B, I would have to go underneath that. That's the situation we've got here. 0 is here, 4 is on the right hand side. In order to get from 0 to 4 in an anti-clockwise direction, I would have to be underneath. I know that. Below the chord. Next thing to work out, am I talking about a major arc or a minor arc? Well, that comes down to the size of the angle. The size of the angle is pi on 6, which is less than pi on 2. Therefore, I'm talking about a major arc. Well, let's define it a bit more. I want to know the equation of that circle. I've marked in the number 2 there. Why? Because I'm going to now try and find the centre of this circle. The midpoint of the chord then becomes a very important point, because I know perpendiculars from the centre will bisect the chord. So I want to know the point where that chord's bisected. And then I know the centre will be directly underneath, because the perpendicular from the centre, well, my chord's horizontal, so the perpendicular would be vertical. The centre must lie on this line. How did I know the centre was below? Well, I'm talking about a major arc. So the centre's got to be on this side of the chord, not on the other side of the chord. I know the x coordinate of my centre. I now want to work out the y coordinate. There's another piece of circle geometry we can do. Well, obviously the hypotenuse would be r. If I can work that out, I've got the radius of the circle. But the other piece of circle geometry, you may recall, the angle at the centre is twice the angle at the circumference. Now, because I'm splitting the angle of the centre into 2, then the angle in the right angle triangle must match the angle here, pi on 6. I can now do a trick. The y on 2 is tan on 60. I end up with 2 root 3. Well, I've said y is 2 root 3. I probably should have said the absolute value because we're below, so it's going to be a negative number. But I've now got the y value of the centre. And the radius? A bit of Pythagoras. And the radius turns out to be 4. We've got enough information now to describe our shape. Maybe I went crazy. The locus is the major arc of the circle, and I gave the equation of the circle there, formed by the chord joining 0, 0 and 4, 0, but not including those points, because that's where the rays start, so it doesn't actually include those points. I suppose another way you could have said that is the equation of the circle, but then said y is less than 0. Because you're saying, it's a bit below that. I mean, that probably might have been a neater way of writing it. But we need to describe it fully. All right, now, looks like a lot. This last one here, the HSC questions, which I've added on the end, I think I did about 20 years worth of questions or something. I think it was 20 years worth of questions there. You can save that when you're getting ready for assessment tasks. If you want to look at some of them now, there's more of these exercises that I want us to do now.